All right, we are going to be rewriting exponential models today. So we're going to be using our properties of exponents to rewrite exponential models to be able to solve problems and give us information about problems. So first here, we're just going to read exponential models can be written in equivalent forms to reveal new information. You can use this technique to determine the rate of growth or decay for different time scales. So meaning, let's say I don't want to look at what it does per year. I want to look at what it does every 100 years or every 10 years or every half a year or every month or every day. Like every day, how's it changing? And that's what we're going to be looking at, is how to rewrite our exponential functions to get that information. So here we're going to be looking at the population of Tiny Town. It's currently 4,000. So that's our starting point. It's increasing as shown. So here it says the population of Tiny Town is growing at a rate of 3% per year. So this is an exponential growth function. So we want to write an exponential growth model. F of t equals a times b to the t, where a is the initial amount. Well, we know my a. There's my a, is 400. B is the growth factor, and t is the time in years. To write a function, so we want to write this function. Okay, so this is a growth model. So it's increasing at a rate of 3% per year. So this is growth. So I know my rate is 3%, which is 3 per 100, which then ends up being 0.03, and that's growth. So that's how much it's growing. So that's what I want to, my growth rate would be 1 plus 0.03. So my function, my f of t, is going to equal the initial amount, which is 4,000, times 1.03 to the t. Okay. So there we have a growth factor of 1.03. So 1.03 is the growth factor. The growth rate is 3% because that's how much it's more than 1. Okay. Right. So this is when t is per year. So here my t is in years. So if I want to know what's a population after 2 years, 3 years, 4 years, so forth, so on, I put in a 1, 2, 3. Okay. So next we want to take the same equation and we want to rewrite it. So then we get the decadal growth rate. This comes from the word decade, which a decade is 10 years. So I want to now come up with the decadal growth factor. Okay, we'll call that D. Hey, my annual growth factor is 1.03. This up here was the annual growth factor, how it's growing every year. To find that decadal growth factor, we take this annual one and we raise it to the power of 10. So I would take that 1.03 to the 10th power. That is like a 10. And that is the decadal growth rate. Sorry, decadal growth factor. That's the decadal growth factor. So if we take my calculator, come on, calculator, and I take 1.03 to the 10th power, I get approximately 1.344. We'll go 1.344. Okay. So that's the growth factor. So the growth rate, this is 0.344 more than 1. So that tells me this is my growth rate. The rate at which this is growing is 0.344, which is 34.4 if we go to percents, 34.4%. So this tells me, okay, the difference here. This 3% is how much it's growing. It's growing 3% per year. This 34 tells me it's growing at a rate of 34% per decade. So it's growing by a rate of 34% per decade. So we can write, for this part C, use your result from part B to write a function that models Tiny Town's population, g of t, where t is the time in decades. So if you notice the difference, this equation that we have up here, t is the time in years. T is the time in years. Down here, T is the time in decades. So this new function we're going to call G of T would equal still our starting amount, our new decadal growth factor, which is 1.344 to the T. And this is, instead of my input being in years, this input is in decades. So this will tell me what's the population 10 years, 20 years, 30 years, but I put in just 1, 2, 3. So when I put in, like if I'm looking for G of 4, this 4 is actually 40 years because that corresponds to 4 decades. Okay, so it's just a way of analyzing what happens as we're looking at larger chunks of time, decades as opposed to individual years, if this model was to hold. Now, this next bit, we're going to go to smaller amounts of time. So instead of dealing with a decade, we're going to look at a monthly. And if you don't remember, there's 12 months in 1 year. So if we want to find the monthly growth factor, okay, we take our yearly growth factor and we're going to take it to the 1/12th power. Because a month is 1/12th of a year. 1 month is equal to 1/12th of a year, because 12 months is 1 year. So we take it to the 1/12th power. So we grab our calculator, and again, we take that 1.03 to that. Now I'm going to put this in parentheses. Oh, it didn't get my division. Delete 1 divided by 12. And I get approximately 1.00247. Okay, so then this is the growth factor. But that growth rate is just how much more than 1 we are. The growth rate would be 0.00247, which if I multiply that by 100 to get a percent would be 0.247%. Barely anything. Such a tiny, tiny, tiny amount. So this tells me, I should have switched colors here, that from up here, it grows at a rate of 3% per year, 34% per decade, but only basically a fourth of a percent, because this is approximately 0.25% per month. So my population is going up by a fourth of a percent per month. And then we can write a new function, h of t. Here, use a result from part D to write a function that models tiny town's population, h of t, where t is the time in months. It'd be 4,000 times 1.00247 to the t. But now this t is in months. What's the population after 3 months, 4 months, the shorter amount of time? So as the units of measure for time increase, as we go from months to years to decades, what does the corresponding growth rate do? Well, the month's growth rate was approximately 0.25%. The yearly growth rate was 3%. The decade growth rate, if we come up here, was 34%. So that growth rate increases. And that makes sense. If we're talking about population, the growth rate from month to month isn't going to be as much as we look at from year to year. And it's going to be even more if we go from decade to decade. Okay? Because they're larger spans of time results in larger growth. And the same would hold true if this was a decay function, which this next bit. Suppose the population of Tiny Town was decreasing at a rate of 2% per year. So what would the function model population of time as t is measured in years, in decades, in months? So let's do years. Again, we're going to start, so that original function we had as f of t. Still a starting population of 4,000, but now instead of adding 2%, which 2% is 2 per 100, which is 0.02. We need to subtract 0.02. So we have 4,000. 1 minus 0.02, which 1 minus 0.02, 0.98 to the t. So the growth rate is, so our growth rate there was 2%, and there's our function. Okay, so our growth factor is 0.98. Okay, so now, because it's 0.2% less than. All right, so now let's do for a decade. So there are 10 years in a decade. So I take this 0.98 and take it to the 10th power. 0.98 to the 10th. I now get 0.817, which is that growth rate. So I can write my function. What did we call this one? That was a g of t, I believe. Yep. So g of t is going to be equal to 4,000 times 0.817 to the t. My growth rate, to figure that out, I need to take the 1 minus the 8.17. Take 1 minus, go up and grab that one. So it's about 0.18, which corresponds to 18%. So here it's about 18% if we go the decade. And then if we go monthly, we take the 0.98 to the 1/12. 0.98 to the parentheses around it to make sure, to the 1/12. 0.998. So my function, h of t, would be 4,000. 0.998 to the t. So I take 1 minus that 0.998 to find that growth rate. 1 minus that. And we would expect it to not be very big. 0.0017, if we round, 0.0017, which is going to correspond to 0.17%. Okay. All right, now we're going to go ahead and we're going to do this again. Here we have the value of a collectible is $25. So there's my initial value. There's my A. There's my A right there. Its value increases, so this would be a growth by 8%, which would be 8 per 100. Percent means per 100, which is 0.08. So 0.08 is that growth rate. So show the model where t is measured in years. Okay, so this is just our general function. F of t would equal initial value of 25 times 1 plus 0.08 to the t. So my function ends up being 25 times 1.08 to the t. So there it's measured in years. Measured in decades, I would need to take my 1.08 to the 10th. So I take my 1.08 to the 10th, and I get 2.15. Yep, 2.15. So my new function here, g of t, 25 times 2.15 to the t. So that growth rate in decades, okay, so here this was an 8% growth rate. This one, I would need to figure out how much more than 1 is this. So I'd have to take the 2.15, subtract the 1 off, and we would get, what, 1.15? So that'd be 115% would be my growth rate for a decade. Okay. And now for month, h of t, so I take this 1.08 now to the 1/12th. We get 1.006. So 25 times 1.006 to the t. Again, now this is months. So the growth rate there, this is more than 1 by 0.006. So this would be a growth rate of 6%. Oh, sorry, 0.6%. 0.6 multiplied by 100, 0.6. Okay, so again, we would expect for monthly the growth rate to be smaller than for a decade. All right, last one. We are going to figure out how to write things in half-life form. Okay, half-life form, here a scientist has a sample of radioactive material for which the rate of decay is known. We know the rate of decay. It says it over here. It decays at a rate of 87.5% per month. So that's how much it decays per month. Okay, so it decays at that rate per month. So I can create, I can create a function for this. And we start with 300 milligrams. So I can create a function for this. F of x equals, I start with 300 milligrams, 1 minus 0.875 to the x. So 300 equals, well, let's take that 1 minus 0.875, 1 minus 0.875, which gives me 0.125 to the x. So this will give me like every month, after 1 month, after 2 months, after 3 months, right? We want, what is the half-life form? What is the half-life form for the exponential decay function? Okay, half-life form is a function where the base is 1/2. A times 1/2 to the x, or 1/2 to the t, okay? Where the base is 1/2. So I need to rewrite this to look like that. My base here is 0.125. I need to get it to 1/2. First things first, I'm going to write this base as a fraction so I can compare it to the fraction 1/2. So if you don't know what 0.125 is as a fraction, I can go in my calculator, I can hit the math button, convert to fraction, and I get 1/8. So this is a fraction becomes 1/8 to the x. Again, my end goal is to get it to 1/2. Well, 1/2 can be written as 1/8 because if I multiply 2, if I look at my cubes column, 2 to the third is 8, and the numerator 1 to the third is 1. So if I take 1/8 here, I can rewrite it as 1/2 to the third. 1/2 to the third is 1/8. This is what we call getting them to the same base. We are converting them to the same base. We want them both to a base of 1/2. And you can try your calculator out too. There's no quick, like you kind of have to trial and error. But if I take 1/2 to the third power, look what I get, 0.125. And is that what we started with? 0.125. So I'm just replacing 0.125 with something that it's equivalent with. 1/2 to the third is the same as 0.125. So, but everything else needs to be equivalent too. I still need the 300, and I still need that x. So I have to take this whole thing to the x power. But I was able to get this now into a base of 1/2. So from here, I just need to simplify a bit or use my power of exponents. A power to a power, a to the n to the m is equal to n times m. You multiply those exponents. So I would multiply this 3 and this x. So my new equation becomes 300 times 1/2 to the 3x. So now I was able to get my base to that 1/2 like we wanted. 1/2 to the 3x. So there I was able to get it into half-life form. Now my exponent, of course, isn't just x, it's 3x. So I have to multiply the exponent times 3 first. So if I want to know how much is left after 5 months, I would have to take 3 times 5 and take 1/2 to the 15. Okay.